Good morning, everyone. Thank you for joining us for this webinar. Today, we are presenting the winning projects of the 2023 Heat Pump Award. The Heat Pump Award, just to give you a little bit of a background, was launched in 2011 with the goal of recognizing the projects that are applying heat pump technology in different sectors. We have the tertiary, commercial, and residential sector, but also depending on the category on which you apply with your project, there's the heat pump city of the year. So we promote and give the award to projects that are applying heat pump technology on a specific city with the help of the city. And then we have the Carb Industry Award. So it's heat pump projects that are applying the technology in the industry sector. The Decar Building Award category, where we award projects that apply this technology to buildings, as I said before, residential, commercial, and tertiary sector. And then we have the Lighthouse Heat Pump Award. So this is, I would say, one of the most special categories, because this is a category that we decided to add to award those projects that are not really in line with the other categories, but apply, let's say, creative and unique solutions to a problem using specific techniques, technologies, and systems, always with the deployment of heat pumps. And last but not least, we have the People's Choice Award category. This category is awarding the most popular heat pump project, which is elected by the audience, the general audience, via a public vote. To give you an overview of today's webinar, we will start with my little speech introducing the Heat Pump Award, and then we will proceed with the keynote speech by our 2024 sponsor, which is Frascold. And then we will start with the presentations of the winning projects. We will start with the world's first CO2-based energy network. Then we will proceed with the water loop heat pump for heating system retrofit in existing buildings. The network heat pump heating and cooling complex to decarbonize homes. And last but not least, the AHT Rottenman decarbonization project gas boiler replacement. And the last 10 minutes of this webinar we will have a little Q&A. So if you have any questions you'd like to ask to the speakers, please just write them in the chat, and I will take care at the end to read them out. Always specifying the person, the speaker you are asking the question to. So as you may have noticed, this webinar is recorded, and you will have, as I said before, the opportunity to write on the chat questions, comments, thoughts, but you have your camera and mic off. The recording and also this presentation that I'm currently sharing on the screen with you will be shared tomorrow via email, so that you have all the material that you may need. That being said, I welcome our sponsor, Frascold. Our keynote speaker today is Kevin Norris. He graduated from Politecnico of Milan with a degree in energy engineering, and he was previously a part of Frasco's R&D department, where he developed a strong technical background. He has always had a keen interest in technical sales and market understanding. Now he's an application engineer in the sales department, and he works to bring market demands into product development and to assist customers in creating new products to support the energy transition and meet decarbonization targets. His personal motto is capturing the world's beauty one click at a time, fueled by wanderlust and a passion for photography. Kevin, I leave to you the floor.
Thank you, Martina, for the nice introduction and presentation. I took control of the screen. Okay. Hello, everybody. Thank you to being here for this webinar. As said by Martina, I'm Kevin Norris, and today I will try to give you an overview of the development in terms of compressors for heat pump. Just looking looking to the agenda after an introduction of Frasco as a company. We'll go deep in the optimization of the compressor for the new markets that we are facing, the industrial market for heat pump and heat pump at high temperature. Just very few words about Frasco. Frasco is manufacturer of compressors, screw compressor and reciprocating compressor. It is based in Italy, close to Milan. We have high surface of production, 53,000 square meters of production, in which we have a vertical production starting from the machining up to the assembly, test lab, and everything in the headquarters. We have a capacity production of around 70,000 compressor by year, and we have a global presence with many partners around the world, and the sales company that we have in United States, in Florida, in India, at Ahmedabad, in China, in Shanghai, and the new sales company in Vietnam for the Far East market. We have also a couple of production outside Italy for the local market, one in India and one in China, of course. Diving in the topic of today, we find out some market requests from our customer that are already in the heat pump market since some years. We have a company that started its production from the refrigeration market, but since 10 years, something like that, we dive in the heat pump market. And some customers start to ask to give up the request to have to achieve sustainable target in the industry to decarbonize the industrial heating sector. And the main topic is to replace fossil fuel boiler, not only in the residential market, but also in the industrial market. So how we can achieve join with our customer this target? The idea is to take the proven technology from the domestic sector at, let's say, low temperatures up to high temperatures, high sides in industrial processes. This is a slide that I think that everybody already know, had already seen. Every time I am in a webinar or in a conference talking about heat pump and industrial heat pump, someone put it in the screen. So I'm the first, I put it on the screen. It is the total energy demand in Europe. And as you can see, the demand for process heating cover 60% of the total demand. Going more in detail, divided it by temperature, we can find out that the total demand below 200 Celsius is more or less 40% of the total in the process heating. So we can say that is a huge part of the total demand of heating. And this part can be covered by the heat pump. Of course, now in the market, there are heat pumps below 100 Celsius. That is what we have already on the market. The idea is to develop a heat pump that can cover also the next step, above 100 kilowatt. This is why we start to develop a compressor able to reach this high temperature. Of course, considering the sizes, our focus was more on bigger compressor. So the development is focused on screw compressor that in our portfolio are the biggest part of the portfolio in terms of capacity, in terms of heating capacity especially. To give you an idea of what is now in the market, which is the target, the roadmap of the development, we can say that now with R290, this presentation is more focused on hydrocarbons, but we have also some reference in synthetic refrigerant. With hydrocarbons and let's say synthetic refrigerant that are actually in the market, is it possible to develop heat pump up to 65 degrees of supply temperature. So the living fluid temperature can be up to 65. With fluid with low density like isobutane, ZD, HFO, ZD, 515B, so low density refrigerant, it's also possible with the standard technologies to reach up to 90 degrees in supply temperature. The development now start to have temperature higher than 100 Celsius. It is necessary to have new technologies. This is why we are developing two steps of screw compressors, one able to develop deliver supply temperature of the fluid up to 140 with the ZD or isopentane, and the last development of the screw compressor that is able to deliver supply temperature up to 160. For this very high temperature, it is probably the fluid that can be the best one in terms of capacity, and efficiency can be only isopentane. First step, say the 140 degrees in fluid temperature. I just reported a typical application point that can be the source temperature of the system. So 65 of evaporating temperature needed to be a source, maybe waste heat recover. So having a very high temperature in the source and 120 in condensing temperature. With the ZD and the isopentane, it is possible to have this target. And with our compressor, we can have more or less a little bit less than 1 megawatt in heating capacity. The second step of the development, 160 in fluid temperature, reported only the isopentane. The condition can be even higher, so 85 in evaporating temperature, source very high, can be waste heat or in some case a cascade system, so a lower stage that can deliver or can be used as source for the high temperature heat pump, and condensing temperature 160. Isopentane, in this case, the capacity are a little bit smaller. We can reach up 100 kilowatt in heating capacity. Of course, the capacity and the COP are very dependent on the condition. Just give you an idea. Application envelope, of course, the application envelope can be very flexible. In this case, you can see the isopentane application envelope. The light blue one is for the first step of the development, the one that can cover the application up to 140. And in the dark blue, you can have the application envelope for the second step of the development up to 160, 165 in condensing temperature. So as you can see, there is flexibility for this kind of compressor. Of course, it is necessary to understand where is the request of the final customer and to understand which is the best option in terms of compressor technology for this kind of application. A very brief overview. I don't want to go very deep in technical details, but basically to design a screw compressor for this very high temperature, basically we just keep the external cast iron. We change all the internal components, the mechanical components, the electrical components, all the gaskets, and of course the pillars of the development was the motor, because as you may know, the semi-hermetic compressor has the motor inside the body of the compressor. So it is quite challenging be able to cool down the motor windings at this high temperature. So it was one of the pillar joined with our supplier of motor to find out which is the best motor that can withstand this very high temperature. Of course, the oil, that is the other pillar of the development in compression design. So we choose the perfect oil that can deliver the correct viscosity in all the application envelope and in all the condition to be sure that the compressor can be reliable during the time. And for guarantee another time the reliability, we find out that we have to change the material of the bearings and increase the clearances between the rotors and between the clearances. We have already some field tests running for the first step of the development, 3 projects in Europe and 1 in China. Up to 135 in condensing temperature with different refrigerant, with a couple with HFO's ZD and 1 with isopentane that are still running with quite good success. And 2 projects that is ongoing for the second step up to 165 in condensing temperature. One is with a well-known research institute in Europe, the Danish Technical Institute. They have a big lab in which they can have the test for big sites also at very high temperature. We are pretty confident to finish this test in the third quarter of this year. There are also some other projects in the design phase. With this series, with these prototypes, we have many requests from different parts of the world. So at the moment, we are in this phase of prototyping development. We expect to validate this series within this year. So to have commercial availability of for everybody, let's say, from the 2025 to the start, the Q1 of the 2025. Thank you for the attention.
Thank you, Kevin, for your presentation. We will now, oh, sorry. Okay.
Oh, sorry.
We will now introduce the award winners of 2023. And we start first with Alberto Mian. He graduated in energy engineering from the University of Padua before moving to Switzerland to complete a PhD in energy at the Swiss Federal Institute of Technology in Lausanne. Alberto co-founded Exergo in 2018 to bring the CO2 network technology invented at HPAward to the district heating and cooling network market. His passion is to industrialize breakthrough innovations while finding their market sweet spots. As the CEO of Exergo, he leads a team of sales and engineers dedicated to develop CO2 network projects, thus contributing to the adoption of medium to large scale heat pumps. His motto is "Don't forget the exergy balance." Alberto, the floor is yours.
Thank you very much, Martina. Hello, everyone. Thank you for having me here. So today I will present you the world's first CO2-based energy network that Exergo has developed and has built and demonstrated here in Switzerland. Exergo, born as a startup spin-off company of HPAward in 2018. And if the mission since the beginning has been to solve a real industrial problem, so to bring this technology and be able to solve a problem that municipalities, utilities, and cities have. Next slide, please. So when it comes to deploying new district heating or to revamp and install large-scale heat pumps to existing district heating, there is a specific problem, which is dealing with the pipe infrastructure and the deployment of large diameter pipes. As soon as we speak about district heating and cooling with simultaneous heating and cooling needs, so there are two possible options with water, 4-pipe system or 2-pipe systems. And this end up in deploying, if we speak about a new installation, 4 pipes, Barry pipes in a city center or in a dense urban areas. It takes time, it takes space, it takes money. When it comes to plugging new heat pumps, large-scale heat pumps in existing district heating, we see all around Europe many projects dealing with revamping of an existing district heating and plugging heat pumps instead of substituting gas-fired boilers with large-scale heat pumps. Often the problem about moving is sourcing the heat pump. So exploiting a lake, a river, a geothermal site, and moving this low temperature energy to the heat pump. Again, it can result in the need of building bulky and expensive infrastructure. In the historical city centers, this problem is also the reason why a lot of projects they do not see light, and many utilities they finally decide to not address the increasing cooling needs in the city centers, and they end up keeping burning fossil fuels in specific historical centers. So Exergo is born with the idea of solving this specific problem. If you go to the next slide. So the basic principle is to substitute the thermal fluid to perform the thermal exchange and move the low temperature energy. We do not rely in water, but we use CO2 in a closed loop, and we use evaporation or condensation of CO2 to absorb or release energy between 0 and 25 degrees C. So we use CO2 in the subcritical state. And this has the advantage that the combination of high heat of vaporization and high density of the fluid allows to exchange much more energy with 1 cubic meter per hour of CO2 that evaporates or condensates. So, so the squeezing down of the pipeline infrastructure has been our accelerator. And using flexible pipe has been really an element that we have demonstrated in this project in Sion. So Exergo has coupled the HVAC supply chain with the oil and gas supply chain, because we are able to move CO2 in this flexible plastic reinforced thermoplastic pipes at pressures that can go between 30 and 64 bars. Next slide, please. So in synthesis about the solution, before to dig into our demonstration project in Sion, we have created a loop for sharing heat from the environment or from waste heat. The system can deliver both heating and cooling. And thanks to this closed loop, we are able to maximize the synergies between the buildings and exchange the energy bidirectionally. I should say exchange the energy. So sourcing decentralized heat pumps, cooling down users, recovering heat from data centers, supermarkets, ice rinks, and any other heat that is heat emitter. An important thing is that we connect to standard HVAC equipment. So we bring a solution that can be plugged to the existing market of heat pumps. So we are able to link our installation with water market available heat pump, cooling heat exchangers, water-cooled chillers, and many equipment that is available in the market. Next slide, please, Martina. So the demonstration in Sion is a project that was funded by the Swiss Innovation Agency back in 2020. It was also saving Exergo just right before the pandemic. So we must really, I should thank a lot InnoSwiss for this making possible this project. The project is located in Switzerland in the canton of Wallis. At the University of Applied Sciences in Sion, which is called the Energypolis campus. So the system has been installed during the pandemic, so the challenge was doubled, and it has been operative since May 2022. In Sion, what we do with our R&D and industrial partners is that we exploit the underground water and the waste heat from a data center to supply heating and cooling to the 3 buildings of the Energypolis campus. The source temperature is available between 5 and 11 degrees C, so it fluctuates during the year. And during this year, so what we do is that thanks to a central plant that is located in one of the buildings, we are evaporating or condensing CO2 and moving this energy to the 3 buildings in order to provide heating and cooling. The total capacity, so the line is sized for, can move up to 1 megawatt, but we have plugged heat pumps for a total heating capacity of 380 kilowatt, and for a total cooling capacity of about 450 kilowatt. We must also say that this installation doubles an existing connection to a 4 pipes district heating and cooling network that is present in the site. Next slide, please. So if we see how the system works, in winter, we are cooling down the underground water, in this example from 12 to 9 degrees. We are vaporizing CO2 at the central plant, and we are distributing the CO2 at the user substations, where the centralized heat pumps are converting this 7 degrees to the supply temperature of the building. So first, it means that we can generate heat at any temperature from 35 to 100 degrees C, and even more if we will use the compressors from Cavan. Thanks to, so that heat pump is condensing the CO2, and the CO2 is pumped back to the central plant where the cycle restarts. In the summer mode, the flow in the circuit is reversed, and the system behaves more like a pumped refrigerant system that we can see in refrigeration. So in that case, we are using the source, we are heating up the groundwater to condense CO2, pump the liquid, and distribute it to the user substations, where we have the CO2 evaporation and we are able to cool down a water circuit that is then going to the floor cooling or the air treatment units. Then in the next slide, we see that one of the interesting the peculiarities of our system is that in mid-season or in periods where we have heating and cooling, we can really enhance the synergy of these demands. And so a cooling user or a waste heat emitter like a data center, what we see in building 19 is in part of the cooling load in building 19 is coming from a data center. So we are generating the vapor there, and the vapor can be used, the gas CO2, the vapor can be used by the nearby heat pump, the water-cut heat pump, or it can be moved to the neighborhood where another heat pump could condense this flow to generate hot water or heating. Next slide, please. So concluding, if you look at the numbers, so I just said there was heating and cooling, and what we have measured after the first year of operation is a production of almost a little bit more than a half a gigawatt hour of heating, almost 0.4 gigawatt hours of cooling, for a total of almost 900,000 kilowatt hours. About the electricity consumption, of course, the majority of the electricity consumption is the one of the heat pumps with 124,000 kilowatt hours. It was also important for us to show that the distribution, one of the other advantages that we bring in terms of operations, is that the pumping energy for moving this low temperature heat is pretty low. The pumps and auxiliaries in Sion have consumed 40,000 kilowatt hours to move this energy, so to deliver the 900,000 kilowatt hours. So the global COP for the heating, if you consider a global COP heating and cooling, was of about 5.5. Of course, this depends on the performance of the COP of the heat pumps. We selected to have two CO2 transcritical heat pumps because we wanted to give the priority to a non-toxic natural refrigerant. And but we have seen that with other machines we could have enhanced also this COP. And then we see that significant proportion of air heating with fresh air and high temperature departures is also affecting this COP. So if we go to the next slide to conclude, so what I can say is that thanks to this in this project we have really demonstrated the fully satisfactory operation of the CO2 network. We had no intervention required. From the point of view of the regulations, we are also compliant with the existing regulations in a public site. So we were able to build the system with any problem in this sense. After this 1 year of operation with the energies I have showed you, we were able to cover almost 80% of the site yearly energy consumption. This also tells us that sometimes we need to think when we are sizing heat pumps and the systems. So we have seen that the installation, the undersized installation was able to cover much more energy than we expected. The installation have been adapted to the conventional rooms, and thanks to the exchange with our partners and the suppliers, it was really nice to see the validation of the concept with industrial players. So to summarize, we have demonstrated the efficient transportation of low temperature energy sourcing for heat pump and cooling users. And it made the difference in our commercialization plan because thanks to this system, we have made visits. I invite any of the people present today to ask us for a visit. We were able to trigger a lot of commercial projects with Swiss and European customers. Thank you very much, and I'm looking forward to answer any question.
Thank you, Alberto, for your presentation. We can now move on to the next speaker, Ilario Zanetti. He obtained his engineering degree from the University of Trento. He has 20 years of experience in the field of low energy building design, and he's the co-founder of Sintec Associati, an engineering studio located in Trentino Alto Adige, Italy. He's now involved in training pre-sales officers and consulting in Innova as marketing engineer manager. Innova is a company dedicated to the conception, development, and production of innovative solutions for heating, ventilation, and air conditioning through the union of technical skills and creativity, technology and design, Italian passion, and international vision. His motto is, "You can't solve a problem with the same mind that generated it," by Albert Einstein. This motto has always accompanied him in his work. He is introducing and presenting to us the water loop heat pump for heating systems retrofit in existing buildings, winner of the Decarbonization Award 2023. Ilario, the floor is yours.
Hello, Martine. Hello, everyone. I think that I have a problem with my cam, but it's no problem. It's okay, my microphone?
Yeah, your mic is on. We can hear you very well.
Okay.
So it's fine even if your camera is not working. Although it's a pity we don't see you.
Hello, everyone. It's a real pleasure to be here today and present a new heat pump terminal for retrofit system in existing building. You can text. Which is the context? Heat pump will play an important role in electrifying the heat load. Decarboning the heat load of building is the key factor in achieving energy and climate goals. If I see the picture with data from European Building Stock Observatory, I see for the next decade, we see the slowdown in growth after 2020 with a gradual stagnation of new building in the long term. Respect the renovation and building replacement will be predominant. And by the end of the decade, I expect 35 million buildings could be renovated. In the next slide, in this context, heat pump will play an important role in electrifying the heat load of building, but I have to solve one important aspect, to find a solution to extend the use of heat pump as far as possible to the market of existing building. For example, condominium, multifamily building, historical or art buildings. In fact, there are several technical obstacles that restrain the use of heat pump in this building as a direct generation system. Usually, the distribution system is generally an insulator or will pour insulate system with existing piping supplied at high temperature, and that means heat losses in distribution piping, and the heat pump want to work a very low temperature. Then I have difficulty in working on existing pipeline, and usually in this multifamily building, for example in condominium, I need for continuity of housing during the war because the people cannot leave the apartment during the war. In the next slide, I see the system. Quindi, in particular system, the water loop system. The water loop system is made up of a closed hydraulic circuit, in particular the existing plant, with two pipes maintained at neutral temperature thanks to the dissipation of thermal integration system. These act as a source for the new terminal. So in the place of a radiator, I place the new terminal, water loop heat pump terminal, positioned in the room to be air conditioned. So in heating mode, the water loop heat pump terminal take energy from the ring, while in cooling mode, the water loop terminal input into the ring the energy. In the next slide, quindi does not require any external drive, total absence of installation constraints, very high efficiency because I use the high temperature in the source, constant terminal output and independent of external temperature, installation on the existing system, and the required water flow rate is modest, especially in air conditioning. In the next slide, there are the main features of the WLHP terminal. It's like a fan coil, aesthetical design, beautiful, and with small in thickness. On the left side, there are the hydraulic connection. I use the same hydraulic connection of the radiator. I have the source side exchanger and the flow meter vortex, and on the right side, on the top of the control panel, below the electronics and the propane compressor. The propane compressor, the content of the propane content is less than 150 grams. In the middle, I have the like a fan, I have the tangential fan and the internal air battery. So it is condenser in heating mode and evaporator in cooling mode. Okay, in the next, we have a DC inverter compressor that modulates the power in according to the real needs for with the inverter tangential file with PI algorithm maintain the low speed for the optimal set point and maximum comfort. I have a 3-side power range in heating and in cooling from 1.1 to 3.1 kilowatt. So I have a high efficiency because I use a very high source temperature. I have propane gas with very low GWP and design and aesthetic in just 14 centimeters of deep. In the next slide, this is the application example for existing condominium. Is a current situation. Usually I have a fossil gas boiler. I have existing piping with high temperature water circulation, and normally is an insulated piping, and that means very high losses. And normally I have a terminal, high temperature terminal, for example, radiators. And the temperature in the ring is about 15-17 Celsius degree. In the next slide, I see the redevelopment building, where I not change to the pre-existing system, quindi I maintain the existing piping, but I maintain the existing piping at a neutral temperature. So I remove the gas boiler and I install the centralized PDC in the pre-first stage, maintain the existing piping at low temperature. I remove the radiator in the room and I install the new terminal, the water heat pump terminal. So I have a low temperature water circulation, about 25 Celsius degree. I have so low losses in pipelines, and with the new terminal, heat pump terminal, I can have at the same time heating and cooling in the apartment. So in heating mode, I take the energy from the source, and in cooling mode, I put energy in the source. So in this case, I balance the energy water loop. So in this case, I maintain the existing piping, which is very important thing. and the existing piping with a low temperature becomes the new source of the new terminal in the room. So in the next slide, there are several ways for thermal balancing of the loop system. For example, naturally, that can increase efficiency. To warm the water ring in heating mode, you can use, for example, thermal solar panel, photovoltaic panels combined with heat pump, or cold district heating. While to cool down the water ring, you can use in cooling mode, for example, for evaporative tower, or also I can use geothermal energy. Okay, in the same time, which is the design approach, the water loop system, you can change the slide. Okay, thanks. Which is the design approach. The water loop system is proposed when you cannot or don't want to redo the distribution system. The system can be proposed to convert a 2-pipe system in 4-pipe system, and you can use the solution for residential villas, condominium, public building valuable for art or historical, hospital, or hotels without air conditioning or with obsolete system. Another thing, you can produce with the same system hot domestic water. A water-to-water heat pump with storage can be placed in each apartment for the production of domestic water. And this is a very interesting thing, because during the cooling mode, the water heat pump put energy in the ring, and with hot domestic water, I take energy of the ring, so the ring is balanced, and I produce hot domestic water almost gratis. Okay, the next. In this simple scheme is a transformation of 2-pipe system in 4-pipe system, and I remember, I don't touch the existing piping in the building. And in this scheme, I have the centralized PDC, the existing piping with a buffer tank, and in the room, I positioned the different water loop terminal. The advantage is automatic and flexible seasonal switching, the occupant comfort, thanks to automatic switching, because I can have heating mode and cooling mode where and when I need, and adaptation of different exposure of building. The next, I enter in the machine, in the unit, I see the regulation with the smart touch. I can regulation with a smart touch control on the unit or on the wall, with the possibility of control by with app, Wi-Fi, or Modbus. Electronic accounting system allow you to monitor consumption, and you can for the best installation in all typical buildings. I have flow management 2-3-way modulating valve with a magnetic filter, and another interesting solution for cooling mode. In case it's not cooling mode, I produce condensate in the room, in the apartment, and in case it's not possible to drain the condensate into the existing building, I can use an accessory and reinject the condensate into the pipeline, the existing pipeline. I have increase the pressure, the water pressure in the pipeline, and I install in a technical room overpressure system that maintain the water pressure at the normal level. So to finish, the advantage of the upgrade system with the water loop heat pump terminal are heating and cooling with the same system. Also at the same time, in an apartment I can heat, and in another I can cool. Use of existing piping, minimal invasive intervention, reduction of distribution losses, housing continuity, complete room by room autonomy by operation, monitoring consumption, optimal comfort, and the use of renewable energy. Thank you very much.
Thank you, Lario, for your presentation. We can move on to the next speaker, Kat Reynolds. Kat is the customer manager for Kensa Utilities and has over 20 years of experience of working with people from diverse backgrounds in community settings. Her work in energy and utilities began with the award-winning Hit the Streets project. Her background in psychology and people-focused services has prompted her interest in researching human barriers to the adoption of low-carbon technologies. She's now, her motto is, if we can do just one thing today to mitigate climate change, it's stop burning stuff. Very well said. She's presenting the networked heat pumps heating and cooling complex to decarbonize homes, winner of the Lighthouse Heat Pump Award 2023. Kat, the floor is yours.
Thank you, Martina. Good morning, everybody. This is my presentation. We're going to talk about networked heat pumps. As Martina has already said, I'm from the Kensa Group, which is based here in the UK. We are the UK's leading manufacturer of ground source heat pumps. Next slide, please, Martina. So the Kensa vision is around decarbonising heating in buildings by scaling ground source heat pumps in a networked fashion, and we do this by installing them at street by street level rather than just by doing them in individual homes. Each home still receives a ground source heat pump actually within each individual building, but the infrastructure is rolled out in a networked fashion. And this means that the individual customer still has the autonomy of controlling that ground source heat pump within their home or within the building if it is a non-domestic building. And the heat pump itself actually provides both heating and domestic hot water, as well as having the capacity to cool the building as well. And we can utilise that waste heat to increase the coefficiency of performance of the ground source heat pump. Next slide, please, Martina. So in the UK, our government has a very ambitious target of installing 600,000 heat pumps a year by 2028. And currently we're installing at a rate of around about 50,000 heat pumps a year. And the New Scientist magazine estimates that it will take the UK around about 600 years for us to achieve this at the current rate. As you can see, our friends in other parts of Europe are doing much better than us. So we need to do something pretty swiftly and in a major way to catch up. And at Kensa, we believe that networked heat pumps is part of the vision to be able to do this. So that's one of the plans. Ground source heat pumps are a little bit different, and they're a really efficient way for people to be able to decarbonise their homes. They are a very cheap way of using renewable energy to heat buildings. They are cheaper to run than air source heat pumps, generally by around about 250 UK sterling per year, which is around about 10% cheaper than an air source heat pump. And they tend to be a little bit quieter than an air source as well, because there's no fan within them. So they're less disruptive, and they're also a little bit better, easier to maintain because they are not exposed to the outside elements, as they tend to be situated within the building. They also have a longer life. They don't tend to need to be replaced as frequently. In Kensa, our heat pumps have a life of around about 25 years. Kensa itself has been going now for 25 years. We were established in 1999, and we're seeing some of our very first customers now come back to us, having had one of our very first heat pumps for replacement. So we know that they have longevity of life. Next slide, please, Martina. Thank you. So here in the UK, we are very familiar with the gas grid, where we have a number of pipes situated in the ground, and they're owned by a utility company, and we all have a white box in our house known as a gas boiler. And we get billed for every month for our gas use, and we pay a small standing charge every month on our bill for access to that gas network. And that's a familiar concept for us here in the UK. Next slide, please. What we envisage with a networked heat pump is something very similar. So we're still having pipes in the ground, but rather than them being filled with gas, they're filled with a glycol mix. There's still a white box in the house, but instead of it being a gas boiler, it is a ground source heat pump, and you will still be billed for your energy use. Instead of it being gas, it's your electricity charge, and you still pay a standing charge to a utilities company such as Kenza for access to that ground source heat pump network instead of accessing a gas grid. So it's a concept that is really recognisable to the UK population. They're familiar with it, and therefore they understand it and are more likely to adopt the concept. Next slide, please, Martina. Thank you. So Heat the Streets is the 21st century version of the gas network. It was a project that was part funded by the European Regional Development Fund, and it took around about 2 years to complete in all. It was developed here in Cornwall in the southeast of England in the UK, which is where I'm based today. Next slide, please. Thank you. The aim of the project was to demonstrate that we can significantly reduce carbon emissions related to heating in domestic homes, and that this project was very much demonstrated replicability and desirability. We had we were massively oversubscribed. So when we rolled out this project to the people in the village of Stithians, which is a rural off-gas village in Cornwall, many people wanted the opportunity to have a ground source heat pump placed into their home, and we actually had to turn customers away because we had limited funding and limited timescales to develop and deliver this project. We also were able to reduce the barrier of the upfront cost by placing the infrastructure into the highway, which you can see here in the picture on the left, and that means that we were able to charge the customers a standing charge for access to the network. Therefore, they didn't have to pay any of the upfront cost of the infrastructure being placed into the ground, and it was very attractive for future investors. Next slide, please. As you can see there from the chart, we drilled in the highway, and this means that if you want to access ground source heat pumps, you do not have to have large amounts of land in order to be able to put a ground source heat pump in, which is something that previously people have thought they have to have. So we can now access this type of infrastructure by putting it into highways or into pathways, as you can see we've done here in Scythians. And this demonstrates the replicability. So the outcomes for the customers were that 100% of our customers reported that their thermal comfort was either the same or better, and many of our customers had seen reduced energy bills. They had come from expensive electrically powered night storage heaters, LPG or oil, and many of our customers as well had seen improvements in their health. Next slide, please. And many of the customers had said as well, even though we had not charged them any upfront costs, they would have been willing to pay some upfront contributions to the system had they been asked to. The top 3 reasons for engaging in the project were to reduce their carbon emissions, so they had very good pro-environmental behaviours. They wanted to reduce their heating bills, particularly in the cost of living crisis, and because the heat pump was free to them, we hadn't charged them anything for the internal installation at all. The survey that we completed with the customers was conducted between 2 and 8 months post-installation. Next slide, please. So network heat pumps can provide both heating and cooling provision to buildings, both domestic and commercial. And this is Kenza's newest product that's on the market now. This is the Kenza Shoebox NX. Next slide. And providing both heating and cooling to a building, the cost of the infrastructure can be reduced by balancing both the heating and cooling load. And these are some of the cities in Europe where this can be done, and the typologies and archetypes of the building where this can be achievable, where there is both a heating and cooling demand throughout the winter and the summer. And the next slide, please. And that is my presentation. I look forward to taking some questions from you about our project, and thank you for listening and thank you for your time this morning.
Thank you for your presentation, Kat. We can move on to the last but not least speaker of this webinar, Clemens Kaltenbacher. Clemens has more than 25 years of experience in the HVACR industry and has been working in this area for Daikin Austria in the last 10 years. At Daikin Austria, he is responsible for the key accounts and total solutions department and is an expert for commercial and industrial heat pump solutions from Daikin. His motto is, "There is always a solution." I love the positive attitude, Clemens. He is presenting the Decarbonization project with Daikin Industrial Heat Pump Solution, winner of the People's Choice Award 2023. Clemens, the floor is yours.
Martina, thanks for this really cute introduction of myself. So yeah, let's take this positivity and start with my presentation. So just let me begin who we are and where you find us. Daikin Central Europe is headquartered in Vienna. So I'm presenting today from Vienna and representing 16 markets in the Central Europe region. We are meanwhile leading provider for heating, cooling, ventilation, refrigeration products and solution within the region. So if we go a step further, looking into global direction, the headquarter of European region is headquartered in Ostende in Belgium, as you can see, representing 30,000 employees in the region of EMEA within several manufacturing facilities all over Europe. And finally, thinking globally, headquarter in Osaka in Japan, Daikin Industries, representing 171 countries worldwide and roughly 100,000 Daikin employees. So what I'm going to present you today is a unique heat pump project together with our sister company in Austria, AHT. Who is AHT? AHT is the leading manufacturer of commercial freezers and refrigeration cabinets located in Austria, in the middle of Austria, in Rottemann, with several production facilities all over the world. And roughly 5,000 customers serving day by day. And what is their mission? What is their journey? So let me take you and guide you through the journey that AHT is facing the next upcoming years. This journey is guided by Daikin's vision to be CO2 neutral with CO2 emission within 2050. And the dedicated project I want to present you today is the replacement of the existing gas boiler system for the heating of the production and office buildings within the factory in Rottemann. So in this picture, you already can see the realized and installed air-cooled heat pumps. So the project itself consists of a heating capacity of 1.2 megawatt heating capacity. You see 4 heat pump air-to-water heat pumps in the picture on the right side. And I will also show you afterwards the 2 water-to-water heat pumps who are supplying high temperature water above 70 degrees to the facilities. The decarbonization project as such also includes installation of a photovoltaic system. As you can see here, roughly 2,000 kilowatt peak of installed panels means 6,000 pieces or roughly 10,000 square meters of installed modules, which roughly can produce a capacity of 2,000 kilowatt hours per year. What about the project in general? So the solution, the concept, which was realized, is a cascade solution with installed air-to-water heat pumps supplying water-to-water heat pumps to reach a final high-temperature water supply of, for this project, demand 70 degrees. The air-to-water heat pumps are scroll compressor technology with refrigerant R32, and the water-to-water heat pumps are inverter screw technology with HFO refrigerant low GWP R1234ZE. The selection and of the units and the concept foresees the very efficient solution as such. So as you can see on the left side, the numbers roughly above around 2.5 total COP, which is promised with this system. So again, showing the heating plant as such. What is also integrated in the system is a hot water tank of roughly 50,000 cubic meters, which is supplied from the heat pump installation. And in addition, we have power to heat installation components supplied by the photovoltaic installed system. And in addition, to have an additional capacity or dedicated time period of the year, there are existing gas boilers who can also, in addition, supply the heating demand as such if needed. So let me give you some background story introduction of this project. So once we started in beginning of 2021, we had the first meeting with AHT, where they heavily introduced their need to decarbonize their facility in Rotterdam, and they need a drastic reduction or a target to reduce statistical their CO2 emissions. So we had a smooth introduction. We had already some solution talks, and we defined to develop several concepts for their project needs. So AHT submitted a lot of data, their energy consumption of the existing installation plans for all the office buildings and production buildings on their location. So as you can see here, the factory in Rotterdam consists of several buildings, which should in the future be supplied by hot water from the heat pump plant as such. Here in the middle is the existing gas boiler installation, and I can already spoiler, this will be also the installation place for the heat pump installation. So we had several meetings to come closer and closer to the solution which we wanted to provide or finally quote to our sister company AHT. So we defined the location where the machinery room and the installation of the air-to-water and water heat pumps can be possible and easily integrated in the existing hydronic system. What happened in before was there was also a deep analysis and finding phase for possible energy sources. So yes, of course, we had a concept to follow on geothermal energy, river water usage. As you see, there is a small river going dividing the location. We were going after well water usage, also wastewater usage was in scope, but all of these possible energy sources could not really cover the demand of the heating capacity which was needed to supply the buildings for AHT as such. So we found a solution that we said, okay, we had to place the installation place for the air-to-water heat pumps. So we made a proper presentation and had a meeting with the responsible persons and decision makers in HT at the beginning of 2022. There was also then additional meeting with the BMS, with the building management supplier Siemens, how the heat pump modules and units easily can be integrated in a building management system which was provided by Siemens. So as you can see here, there was also deep analysis and concept how the operation of the units can be easily realized. Here you see the air-to-water heat pumps. Okay, you can also see the energy temperature of the energy loop of 15 degrees, which is supplied by the air-to-water heat pumps. And here you see the water-to-water heat pumps, which are supplied by the air-to-water heat pumps and supplying the high temperature of 70 degrees for the facility buildings at AHT. So, okay, we found a solution of sizing the units, also very important. Then huge success to my sole sales colleagues as such, roughly 40,000 euros turnover for this project, for these 6 dedicated heat pumps was found. Great success to the sales colleagues greetings again. Then we also agreed a factory visit at Daikin Applied factory in Cecchina in Italy, where the units are produced as such, where the guys from AHT could join a so-called witness test, where they could realize and join and see which capacities and high temperature the unit can cover. And finally, the delivery of the unit end of 2022. The starting of the commissioning, so pre-commissioning phase started last year in autumn. So there were a lot of hydronic refurbishment works needed and mandatory to be finalized till we could start the commissioning of the first units. And pre-commissioning phase ended beginning of this year, so we could finalize the commissioning phase as such already in end of March, beginning of April. So units are running proper since today. Finally, I want to show you also some pictures from the installation. So here you can see the 4 air-to-water heat pumps. Again, scroll compressor technology, which is leading to very efficient operation in combination with low GWP refrigerant R32 for the outdoor installation. Here's a picture of the water-to-water inverter screw heat pump. When I see this picture, I always got to remember that we also needed to guide and support the technical responsible person from AHT, also to cover all the legal standards and restriction, the local standards for the installation in the machinery room, but not only in the machinery room, also on the roof. We need to follow very strong restriction regarding all the needs to install units with A2L refrigerant, but all these steps we could succeed together very successful to get these units started proper. Here you see some pictures from the hydronic installation. On the left side, you see the pump station for the air-to-water heat pumps. The middle picture shows the energy supply for the water-to-water heat pumps. And finally, the high temperature supply pipes on the right side with the high temperature of roughly 70 degrees. So this is the final picture of the water-to-water heat pump in the machinery room. So both units were in separate, planned to have it in separate machinery rooms so that they can easily take over operation in case of failure or whatever, can easily be managed. So finally, what we were very proud of is that we got the recognition from the HPA awarding Forum 2023 to be the People's Choice project in 2023. It's always good to have a good and great awareness in the market, but it also shows that it is very important, and thanks also to the former presentations and presenters before me and my presentation. And thanks to these unique solutions which are already available with innovative technologies and solution, take these solutions, take these innovative ideas and concepts, go out into the market. We always will be very successful. So I wish you all together the best in decarbonization, the European community. Thanks a lot to the audience. Bye.
Thank you, Clemens, for the presentation and for the extremely nice message. I think I'm speaking for all of us by saying that. So now it is officially time for the Q&A. I saw that in the chat there has been quite an interaction between the attendees and the speakers. I think that there are only two questions left to answer. One is for Ilario, for Innova. Innovate asks, is this system available for households as well, or is there a minimum size for the buildings for multiple houses?
I don't understand, Martina, can you repeat?
Yes, so Innovate asks you if the system that you developed for the project is available for households as well, or if there's a minimum size for the buildings regarding multiple houses, so condominiums.
Okay, you can use the system in all size of building. If you work in a condominium, you can have a better payback, and the difficult normally is don't know the type of plant, so is very important work in synergy with the installer, designer, building manager for know the system and propose the correct solution. For all buildings.
Okay, thank you, Ilario. I think the question was answered. We'll see if Innovate has anything more to ask you. Moving on, we have a question from Rufus Grantham for Kat. You already answered part of his first question, but he also asks if there is enough funding around to develop these projects, which he presumes are to an extent in partnership with the local government.
I must have missed that. Apologies. Yes, absolutely. Certainly, we are working in partnership with, we're privately funded over here at Kenza. We've got much investment, but we're certainly looking at ways of removing the upfront cost barriers to roll this out across the UK and beyond. So yes, we're definitely looking at ways of how we can fund this and how we can tap into pots of funding from government funding pots to be able to roll this out, and how this is going to become part of bigger UK heat network plans. So as part of to decarbonise towards the UK net zero 2050 ambition. So yes, there is ways of doing this, and it's something that we are working on at Kenza and beyond. So yes, the answer is yes. It's just slightly complicated, but it's slow progress. But yes, there is definitely ways of doing it.
Thank you, Kat, for replying. We have, I believe, a more general question to all of you, which is from Tahir. He asks if there is a heat pump solution for places with minus 25 degrees Celsius, and is also interested in knowing if it exists, how efficient is the unit. I don't know who wants to reply to this one.
I can step in, Martina, for this dedicated question, because it could be also product related. Surely it's depending also on the capacity. I have to say, so this question is not really detailed enough to give a dedicated answer. But let me answer like this. So we always need to make a deep analysis when it comes to heat pump solution. So if there is a request to have a dedicated heating capacity and demand at minus 25, we always need to check in the region. I don't know where it is located, but if I go in the Austrian region, and we have also when the Alps, as you all know, so we are a good skiing country. So where we also always need to check the temperature during the year. So as I can assume for this question right now from Tahir, and thanks for this, I would say minus 25, minus 20 in the European region is not that much hours available during the year. So now I'm focused on Austria, for example, or neighbor countries, yeah. And then we are transferring the heating capacity to a realistic number or outdoor temperature in winter. So it really needs to be checked project by project if there is really the need to have the full capacity at minus 25, minus 20, minus 15, whatever is needed or standardized the demand. And after that, we can easily also adapt what happens at lower temperatures. Yeah. So then you have the possibility to have buffer tanks installed. You have the possibility to have electricity heated solution as such, or solutions coming from Kate or Alberto, as mentioned. So there are a lot of innovative solutions which easily can match the question from Tahir. Thanks.
Okay, thank you, Clemens, for addressing these questions. I don't know if any other speaker wants to add something to that answer, but I think not. Okay, so there are no other questions in the chat for now, but I do have some questions for all of you, starting with you, Alberto. If you could say what are the factors that have accelerated the development of your project, and also can the CO2 network be adopted in both hot and cold climates? And I believe this is also in line with Tahir's questions, actually.
Yes. Thank you very much. So first question, there are two main factors that have accelerated Exergo development. So we started with an idea that was coming out of the EPFL, so the Federal Polytechnic School in Lausanne. Without the re-adoption of CO2 as a natural refrigerant, and without oil and gas R&D, we wouldn't be able to have a commercial offer today. So in the first sector, the refrigeration in commercial and industrial refrigeration manufacturers or developers, they have started to re-adopt CO2, a natural refrigerant, together with ammonia, propane, water as a natural refrigerant. And so this has made available all the equipment that we are using. So ball valves, simple ball valves, safety valves, liquid levels, tanks, pumps, all this equipment was on the market the day I founded Exergo. And being able to source this existing supply chain was definitely an accelerator. The second element to complete the answer was really the existence of these reinforced thermoplastic pipes, so flexible pipes that have been developed by the oil and gas industry for the last 20 years that allow to transport safely CO2 at moderate pressures, temperatures up to, so we are in the subcritical region. It wouldn't work for high temperature, but in the subcritical region, there are really solutions that allow to have zero leak on a plastic pipeline where you have CO2. And the fact that these solutions are also used for hydrogen transportation really accelerated us. So concerning the second question, yes, we have a system that with the same technical setup can serve as a mainly heating or mainly cooling. It's just a matter of what are the flows and the terminals where we plug the network. In terms of efficiency and system operability, it's also important to know that we always need to evaluate the source we have so the environment we have around or the industrial environment we have around. So for example, in Dubai or in hot weather countries in south of Spain, we are able to build a mainly district cooling system using CO2 and use the CO2 also to serve decentralized heat pumps for the hot water production or for the small heating production that is needed during the winter. Inversely, in cold weather countries, we can exploit waste sources. We work a lot with we try to really couple waste emitters like data center to enhance, so to provide cooling, but also to have a hot source that is available to the centralized heat pumps. And so especially if air is pretty cold, having a waste heat can boost the COP of the users and enhance the performance. There are also non-favorable situations, so we do not have the solution to cover all the cases, but I'm pretty happy because after 6 years of this adventure, I can say that we have enough sweet spots in both hot weather and cold weather countries. Thank you very much.
Thank you, Alberto, for your answers. I now have 2 questions for Ilario. The first one is, how is condensate drainage done in the summer season in case of non-existing drainage pipes? And the second one is, can one produce domestic hot water independently using the water loop?
See, the first one is the very problem in the existing building because in cooling mode I produce condense and normally I don't have the condensed drainage in the apartment, and in the apartment the work is limited in the apartment. So we have this accessory is a high pressure pump that is positioned into the unit and so can radiate into the system the condensate and without necess the drain condensate in the apartment. Naturally, in the technical room, I necess to overpressure system for control the overpressure, but is a very, very interesting solution. The second question is another interesting solution because the apartment see the existing piping like a source. So I, in my apartment, can decide if it cooling or hot domestic water, because the normal hot domestic water produced in the technical room and work with an insulate piping, I have normally a very high losses in the piping, also in the automated water produced. So if I can produce automated water in my apartment with, for example, a water-to-water heat pump connect similar to the similar water loop heat pump on the existing piping, I can produce automated water when and where I need.
Okay, thank you, Ilario, for your answers. Moving on, I have two questions for Kat. The first one is, out of everything you learned on the Hit the Streets project, what would you say was the most important? And the second one is, are there any types of soils or ground that you cannot drill into for ground arrays and boreholes?
Really good questions, thank you. Most important things learned, I suppose that when we're doing retrofit projects like Heat the Streets, where we're fitting into homes that are already occupied, is to remember that these are homes, not houses, and that there are people living in them, and that every home is very individual to the person. So some of these homes are really hard to retrofit into, so they're quite complex properties, but also the people within them are quite complex. So it's really important to remember when we're looking at network heat pumps and scaling up that, when we're developing that that concept, that we have to be mindful that we've got individual people at the end of every one of those ground source heat pumps. And I think that's a really important lesson to take away, is that these are still people who are decarbonising, and it's not just a concept that we're rolling out to properties or buildings, that we have to bring the people along on the journey as well. And I think that's really important. People have to want to adopt this technology, so we have to make the technology work for those individuals. And in terms of the geology of the ground, no, there isn't really anything we can't drill into. We like quite hard ground, and here in Cornwall, when we did Heat the Streets, we were actually drilling into granite, which is a very hard stone, and we quite like the hard ground, because when we bore hole into it, and we then take the drill pieces back out, it doesn't collapse. So if we drill into things that are quite sandy, as we take the pipes back out to then put the HDP or the MDPE pipework in, it tends to sort of collapse, and it can be a little bit trickier. So we like solid rock if we can, and it also helps with the efficiency of the thermodynamics, and how the how it absorbs the heat from the ground into the actual pipework. So yeah, granite's quite a nice one. Sandy soil and very, very wet soil, not as easy, but not impossible.
Okay, thank you, Kat. And absolutely, the human factor is always very important. I have just two questions left for Clemens. The first one is, did you consider to cover the existing cooling requirements for mentioned buildings also with the solution you presented? And the second one is a year-round heating operation also with high living temperature possible with the solution, even in summer?
Easily, yes and yes. I always let it go for a presentation like that, and it's somehow always leading me that I miss these points. Surely, we also had an analysis on how to cover the cooling demand in the factory facilities and office buildings at AHT in Rotterdam. But due to the fact that the buildings got a refurbishment of the installation, especially for the air conditioning, just a few years ago, so we let these plans go, but they are not left. So there is still a possibility to have a connection to the supply of chilled water for future concepts and plans, for the first step. And for the second question, yes, surely. With this system, we have the possibility to guarantee high temperature supply of above 70 degrees all over the year. So starting, and I shared already a picture to answer also Tahir's question more detailed. We have the possibility to start from -20 to above 35 degrees to cover the heating demand all over the year.
Okay, thank you very much, Clemens. Our webinar has come to its end, so I'm going to let you free for the rest of the day. Thank you very much for attending, and a special thanks to all the speakers for presenting your great projects. I hope that it was a nice opportunity for you to give a more insight into them, and also, why not collect a few interesting contacts? That's always very nice. For the attendees, I just want to give you a quick reminder that the application for the HPAward 2024, are now open. So you can just check out the procedure, the application process. It's very easy, and you find all information on our website. Thank you very much, and have a lovely day ahead. Bye-bye.
Thank you so much.
Thank you very
Thank
much.
you.
Bye.
Thank
Have a
you.
nice
Thank
day.
you, all of us.
See you
Thanks.
next time.
Bye-bye.
Bye.